Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Okay, lecture 96, Calculus Light, area under a curve. So last time we talked about tangent lines, which are related to derivatives, and that's kind of like the first essential idea from the calculus. Another problem that people considered back in the 1600s was finding the area under a curve, right? That's just like a general problem. And so that's what we're going to explore today. So we'll start easy. So here my curve is just a nice horizontal line. That's relatively easy. And so I'm going to consider the area under the curve up to some point. We'll call this point here the point P. And so I'm going to consider the area under the curve between the origin and this point. We'll call it x sub p comma y sub p. Well, that's fairly straightforward, right? So here's the area that we're talking about. Makes sense, right? Who knows how to figure out what that area is? Anybody? Yeah. The area in this case is just x sub p times y sub p. Right? It's fairly straightforward. Okay. Now let's do another problem. Or rather, I'm going to use a different curve. This will be my point P, x sub p, y sub p. Here's the area, and we will say that the line is y equals x. That's a terrible x. Y equals x, right? Now, who knows the area for this shape, if we think of it as a shape?
Half of the length times height.
Yeah, exactly, because we know that if we imagine in our minds this original curve here, right, that we did before last time, we recognize that through symmetry that this area will be half of the previous, right? Because I can always take a rectangle and fold it in half, right? And so I'd say, well, the area is just half of what it used to be. And that is, of course, correct. Now, in past lectures in the last semester, I forget which lecture in particular, I had mentioned that calculus kind of makes people stupid. And it's kind of true, okay? Because solving this problem like we just did takes a degree of cleverness, okay? You have to be clever. You have to say, oh, well, this is just like the rectangle, but if I fold the rectangle like this, I cut the whole area in half. And so I can just take half of the area's rectangle, right? So that takes some cleverness. But let's say I'm not clever. And instead, I do it like this. I'm going to divide this into a few intervals. So I'm going to break this up into 4 rectangles because I know how to calculate areas of rectangles, right? And so I'm going to call the width of each of these rectangles delta x, okay? And the height we're going to get from this equation here, right? So the height will be y times this delta x. That'll be the area of this rectangle. And so I'm going to calculate the area as the sum, or I'm going to write it like this. We'll call this A1, A2, A3, and A4. This is just A1 plus A2 plus A3 plus A4. Yes?
Yeah.
So if this is delta x, right, then A1 is just delta x times y of delta x. That's y is equal to x. That's just delta x squared. Yes? So for the second rectangle, the width is still delta x, right? Because it's this width right here. Yes?
Yeah.
So delta x times y of delta x. I'll just write it like this. Y of not delta x, but 2 delta x, right? Because I'm over 1 delta x, 2 delta x. You see that?
Yeah.
So that's my x positions, 2 delta x. I'll put 2 delta x. I should have written it that way here. Delta x times y of delta x. There, that's better. A3 is equal to delta x again, because it's always the same rectangle width, right? You see that? this width and this width and this width and this width. All 4 of these rectangles have the same width, okay? But they have different heights. So for A3, I need to find this point here, which is just 1, 2, 3 times delta x, right? So it's delta x times y of 3 delta x. Yes? And for A4, it's delta x times y of 4 delta x. Okay? And so if I write this up, I can say that A is equal to, I can factor out a delta x out of all these when I add them all up, right? So A1 plus A2 plus A3 plus A4. So I'll have delta x times, and then we'll have an, well, actually, let me do it like this. Let me just write it out longhand. A is equal to A1, which is delta x, times y of delta x will be, plug in y equals delta x here, I get delta x, right? So I'll write that as delta x squared plus delta x times y of 2 delta x, right? When I plug that in, I'll get another delta x squared, but I'll get a 2 here, yes? Plus, the next one will be 3 delta x squared plus 4 delta x squared. Everyone see that?
Yes.
Now, let me factor out the delta x squared. That's delta x squared times 1 plus 2 plus 3 plus 4. Yes? Now, what is 1 plus 2 plus 3 plus 4? Anybody? 10, right? So this is equal to 10 delta x squared, okay? So what is this delta x? Well, if I said that the whole interval from here to here, if I just call this length x, right, then delta x is just equal to x divided by 4 in this case, yes?
Yeah.
So if I replace delta x squared with x over 4, then that's going to give me 10 delta x squared, excuse me, forgot to substitute it in. It's going to give me 10 over, not 4, but I have to square it, right? Because delta x is squared, so that's 10 over 16 times x squared, which we can reduce, right? Because there's a 2 in both of them. That's going to give me a 5 here. It's going to give me an 8 here, x squared. But let's see, what did we get when we did it the clever way, when we got it? Because you can see we've got a bit of error here, right? This extra area, right, that we've included is not actually under the curve. Do you see that? So our approximation has kind of overestimated the area, right? So let's calculate what it actually is based on what we see here using our formula that we had from before of 1/2, and we'll have x times y equals x at this point, right? That'll be x squared. So 1/2 x squared. Here we got 5/8 x squared. If it was 4/8 x squared, then we have exactly the right answer, right? But it's a little bit more, you see? So we've overestimated the area by 1/8, you see? So what can we do to ameliorate that problem? Well, what if we used more rectangles? That's possible, right? And so if instead of just 4 rectangles, what if I used n rectangles? Where n is just some arbitrarily large number, right? How would this change things? Well, instead of having 1 plus 2 plus 3 plus 4, right, we'd have 1 plus 2 plus 3 plus 4 plus ... all the way up to n, yes? Because we'd have more terms. Do you see that? Because this term would be delta x times y of delta x. This would be delta x times y of 2 delta x times y of 3 delta x times y of 4 delta x, and next would be delta x times y of 5 delta x, 6 delta x, 7 delta x, right? All the way up to n delta x, yes? And so here we have delta x squared times 1 all the way up to n. Does anyone know how to solve that particular problem? The sum of the integers up to n? Anyone remember how to do that? This is a famous problem that allegedly Gauss had solved as a small child. He was given an exercise by his teacher to add the numbers from 1 to 100, and he came back almost instantly with the answer, right? And the teacher was perplexed as to how he added all those numbers up so quickly, and he had found a formula. He found a way to do it, right? First, let me just tell you what the answer is, right? The answer is that the sum of these integers is n times n plus 1 over 2, okay? So if you were to pick a really large number, like say, instead of 4, let's just use like 10, right? So we get 10 times 11, which is 110, over 2, 55, right? So let's substitute in for delta x squared, right? Delta x squared is equal to x over n. So that's x squared over n squared. right? Times the quantity, and we'll put the half over here, and we'll have n squared plus n. Yes? So I multiply this through, what do I get? I get 1/2, well, x squared, and then n squared times 1 over n squared is just 1, right? So the n squared cancels here. But I get a second term with 1/2 x squared. Now I have n over n squared, so this will be x squared over n. Okay? Does that make sense? Let's do that thing that we did last time with the derivatives or the tangent lines, and let's take the limit as n approaches infinity, right? So what is, we'll say that the true area is equal to the limit as n approaches infinity of 1/2 x squared plus 1/2 x squared over n. Well, what happens to this second term as n goes to infinity? That means I'm using an infinite number of rectangles, right? If I divide a number by infinity, what does that become? 0, right? So this goes to 0, and I'm left with just 1/2 x squared. Now, that's exactly what we got when we were clever about this, yes? Yeah. So we've arrived at the same answer using a kind of dumb but robust technique that we could apply to any curve, right? This will work on any curve that we draw. It didn't care that this was the, just a straight, or it's going to be a vertical line. Is that the right term? No. Diagonal line, right? It didn't care that this is a diagonal line, right? We just used the line to get what the height of the rectangle was, right? As long as we have a functional form to figure out what the height of the rectangle is, we can use this for any curve, okay? So that makes it very useful. Before I apply it to another curve, let me show you how to come up with this formula, though, because we'll use this to come up with it for any situation. And actually, if you think about it, it turns out the work is really built into this. And this is actually a method called, I think it's referred to as Newton-Gregory theorem. I'm not going to derive it so much as just show you how it works. And for those in the know, this is kind of like a discrete version of a Taylor series expansion. But let me show you how it works. So here we've got this sum of these integers, right? And let me just sum the first few up. So 1 will be the first one. And then I'll have 1 plus 2. That would give me a sum of 3. And then 1 plus 2 plus 3 will give me a sum of 3 plus 3 is 6. And then 1 plus 2 plus 3 plus 4 plus 5, oops, just plus 4. Right? I'll add 4 to the previous number, so that gives me 10. And then 1 plus 2 plus 3 plus 4 plus 5 will give me 5 plus the previous number, so I'll get 15. Okay? So let me write these numbers down like this. 1, 3, 6, 10, and 15. Okay? And if you've ever seen the Pascal's triangle, it's a similar kind of thing, okay? So I'm going to take these two numbers and generate a new number below it. 3 minus 1 is 2. 6 minus 3 is 3. 10 minus 6. 15 minus 10 is 5. You see, we've gotten back this 2, 3, 4, 5, right, that we had before, okay? So this has given me the sum of the integers. And I have to keep going back with it, though. Okay, so I keep going back until I basically get a constant value. 3 minus 2 is 1. 4 minus 3 is 1. 5 minus 4 is 1. You can see that's just going to continue all the way down, right, as ones. Okay, so here's the trick. We want to use these leading terms here. So I want to figure out what the functional form of this top line is. Okay, I want to get that in terms of n. Okay, where this keeps going, right? This second line is going to go out to n. Okay. And so I'm looking for this functional form. And it turns out that it's going to be equal to, it'll be n, choose 0 times this first coefficient, right? I'm going to call this f prime, okay? Plus n, choose 1 of f double prime, where this term here is going to be our f double prime, and this will be our f triple prime, plus n, choose 2 of f triple prime. And the next term down would be 0, so that would cause this to truncate. That's why it's important that this terminate. So once this stops changing, you get a constant value, right? That's like the last term in this series that we're going to get, right? And so this tells me to use the binomial coefficients, which if you're not familiar with the binomial coefficients, or n choose k, I put out that counting video with the ice cream. You can watch that to figure out how to use them. But I'm actually going to change the form of it because normally this would assume that we start at 0. where n equals 0, then n equals 1, n equals 2. To get the formula in this form here, you really need to start at 1 instead. So I'm actually just going to use a substitution. I'm going to say that m is equal to n plus 1, which means I'm going to substitute in for n, m minus 1, right? Do you see that? Because if m is equal to n plus 1, so I want to start at 1 instead of 0, then I have to change this to m minus 1, m minus 1, m minus 1. Now we just plug in, right? So m minus 1, choose 0. Well, what is that? That's going to be, and first we'll put in this coefficient. F prime is 1, so it's just 1. We don't need to write anything. But we'll have m minus 1 factorial divided by 0 factorial times m minus 1 factorial. These cancel. 0 factorial is defined as 1, so this term is just going to give me a 1. So I'll write 1 down here. The next term, f double prime, is 2, so it'll be 2 times. Now we do m minus 1, choose 1. Will give me m minus 1 factorial divided by 1 factorial times m minus 1 minus 1 will be m minus 2 factorial. So that's just going to chop this off at m minus 1. So this will be plus 2m minus 1. Okay? And then the last term, m minus 1 choose 2, will be multiplied by 1 again because f triple prime is just 1. So that's going to give me m minus 1 factorial divided by 2 factorial times m minus 1 minus 2 this time. So that'll be m minus 3 factorial, which is going to leave 2 terms for this. It'll be 1/2 times m minus 1 times m minus 2. So let's distribute these. That's 1 plus 2m minus 2 plus 1/2 times, I'll just keep the 1/2 here. It'll be m squared minus 3m plus 2. And I'm going to factor a half out of all of this. Well, 1 minus 2 is just going to give me minus 1 here, right? Factoring a half out of all of it gives me 1/2 times, I'll need a 4m for the factor of half out, minus 2 plus m squared minus 3m plus 2. Well, the plus 2 and the minus 2 cancel, so that goes away. 4m minus 3m is just m. So I get m plus m squared, but this is the same thing as 1/2 m times m plus 1, which is what we had before, except I used n's, right?
Yeah.
So that's how you can get these, that's how you can figure out what these sums, these infinite sums are, okay? And as it turns out, I mean, the summing that you're doing in this problem is really being done here. And if you think hard about it, you'll see that that part of calculus is really embedded in all of this, okay? But let's look at a different curve now. All right, this time we're going to consider, instead of a diagonal line, we're going to consider a parabola. So we have the equation y equals x squared. We want to find the area under the curve. We'll put our rectangles in again like we did before, right? So the first rectangle's area will be delta x times y of delta x. The second rectangle will have an area of delta x times y of 2 delta x, right? Why 2? Because we've gone over 1 delta x, 2 delta x, right, to get this value. 3 will be delta x times y of 3 delta x, etc., right? So what would this give us? This would be delta x, y of delta x is just delta x squared, so it's delta x times delta x squared is delta x cubed. Here we have delta x times, we square this, we get 4 delta x squared, so that's 4 delta x cubed. Here we're going to get 9 delta x cubed, right? The next one will be 16 delta x cubed. So you can see what's going on here, right? This kind of a sub n is equal to n squared delta x cubed, right?
Yeah.
And so when we sum all of these up, right, what are we going to get? As I sum all of these areas up, I'm going to get a delta x cubed times 1 plus 4 plus 9 plus 16 plus dot, 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 all the way up to n squared, right? I can replace my delta x, of course, with x over n. So this is really going to be x cubed over n cubed. See that?
Yeah.
But I need a formula for the sum of the squares, right? It's a little different than before. And so we can, just like we did before, I'll construct the table, but I won't go through the algebra. I'll just write the answer down when we're done. And I'll leave that as a homework assignment for you guys to do, the algebra on this. But so how would we begin this? Well, we start by adding up these square numbers, right? So we'll do 1 is the first one, just like before. The second one is 1 plus 4, which is going to give us 5, right? And then the next one is going to be 1 plus 4 plus, the next square number is 9. So that gives us 14. And then 1 plus 4 plus 9 plus 16. That's going to give us, well, 16 plus 14 is 30. And then 1 plus 4 plus 9 plus 16 plus 25 is the next square number. And 25 plus 30 is 55. Right? And if I subtract these, like we did before, right? Remember how we did this? So 5 minus 1 is 4. 14 minus 5 is 9. 30 minus 14 is 16. And 55 minus 30 is 25. So we see there are our squares, right? And then we do it again. Down one more. What is 9 minus 4? That's 5. And 16 minus 9. And 25 minus 16. See a pattern there? Yep. But we're not a constant yet, so we have to keep going down. So 7 minus 5? It's 9 minus 7? Yeah, you can see it's going to be 2 all the way down, right? If you don't believe it, you don't trust it, add another square number in, right? 36 is the next square number. You see that 36 and 55, right? You can construct another row. But we can see this is going to be constant throughout. So now we have all of the things that we need. We need f prime, f double prime, f triple prime, and f to the 4, right? And so you would construct a formula. You do the same thing with n minus 1, choose 0 times f prime, plus m minus 1, choose 1 times f double prime, plus, et cetera, for all of these terms, right? So you've got a 1, a 4, a 5, and a 2 as a prefactor, right? Okay, so I'm going to leave it up to you to do the algebra on this, right? But what you should find in the end is 1/3 m cubed plus 1/2 m squared plus 1/6 m. So if I substitute that back in here and take the limit like I did before, right, with area is the limit as n approaches infinity of x cubed over n cubed. I'm just going to switch m's for n's just so we're consistent. All times this, so it'll be 1/3 n cubed plus 1/2 n squared plus 1/6 n. You can see that the first term, right, the n's are going to cancel out completely, right? And that these other terms will always have an n or an n squared in the denominator, right? So this is going to be equal to x cubed 1/3, just this first term here, right? 1/3 x cubed. Okay?
Okay.
If we were to look at a cubic equation next, can you guess what we would find? Well, let me just summarize where. Right, so this is, I'm going to write this as a of, it looks like a of y equals x squared, right, is equal to 1/3 x cubed. From before, we had y of, let me do this here. Let me kind of summarize the previous two results. For the area of y equals x, right, we found that the answer was 1/2 x squared. The area for y equals x squared, we just found, is equal to 1/3 x cubed. Can you guess what it will be for y equals x cubed? If we were to do that problem and do it exactly like we did it here. Anyone want to guess what the answer would be? 1/4x to the 4th. Exactly. Exactly. Just take this down. If you recall from the last lecture, right, that we had these results that said that the derivative, let me write it like this, d over dx of x to the n was equal to n times x to the n minus 1, right? If I take the derivative of 1/2 x squared, I'll have the 1/2 times the derivative of x squared, which is going to be 1/2 times 2x, which is equal to x. You see that? So the integral is kind of the, and that by the way is what we call this. We call this the integral. But you can think of it as an antiderivative, okay? So if this is the derivative formula we found, and if we do this stuff we did with the area to that, we get this function x to the n back, you see? So derivatives and what these are called integrals, okay? Let me just show you some notation. So before we were kind of writing things like the sum of, we're saying that the area is equal to the sum of f of x times some delta x. We're adding up the area of these rectangles, right? Then we're going to replace this with this sign. It's the integral sign. It's a funny looking S if you want to think of it that way. It's like a tall stretched out S, stands for sum. And we'll write it like this, f of x dx. So we replace the delta x with dx for the same reason we did it before with the derivative. It means it's a really small delta, right? And so we'll replace these sums with these. And we can come up with these general procedures just like we did with the derivatives, right? So we can say, well, the integral of x to the n dx is going to be equal to 1/n x to the n plus 1. Plus a constant. Now, don't worry about why there's a constant in there, okay? But there'll always be this constant term, because remember, the derivative of a constant is 0, right? So you can always add any constant value to it. When you take the derivative, you'll get this back, okay? So this is for what you get for polynomials. You can also have the integral of the sine of x dx is equal to minus the cosine of x plus a constant. The integral of the cosine of x dx, a little more space there, dx is equal to the sine of x plus a constant. And then finally, the integral of an exponential, e to the x dx, is equal to an exponential plus a constant. So these are some basic antiderivatives or integrals. These are technically, they're called indefinite integrals, but don't worry about that. You'll learn all about that stuff when you do calculus. But I like to think of them as antiderivatives because it's just going backwards, right? Anything else on this? I think that's it. The last thing I'll say is that there's this fundamental theorem of calculus, which basically says that the integral of the derivative, f prime of x dx, is equal to the function f of x plus a constant, okay? It's this relationship between the derivative, the integral, and the function itself, okay? And this is, you know, the fundamental theorem of calculus, but you'll learn all about that when you get to calculus. But it's antiderivative. The integral of an antiderivative is the original function, okay? All right, I'm out of time, so that's it.